Then I
Okay,
share.
hi everyone. Hi everyone. Today we have the show Tell of the Pangeo community, and we are very glad to have Alex Kmoch, who is presenting about the distribute spatial systems, and in particular the DGGS systems. Alex is a member of the Landscape Geoinformatics Lab under the Department of Geography of the University of Tartu, Estonia, and he is as well elected board member of the Estonian Geoinformatics Society and a European co-chair of the OGC University Domain Working Group. So you're welcome, Alex, and looking forward to hear about the discrete global grid systems. Yeah.
Thanks very much, Alejandro. I'll share my screen here. Yeah, so as Alejandro nicely introduced myself, I'm Alex. I'm working here in Estonia in Tartu, and I want to tell you today a little bit about discrete global grid systems, DGGS, and their potential impact in geoscience and geospatial sort of in general. First of all, we have already started a bit of a discussion around that. I engaged with Pangeo maybe around a year ago. And sort of we have this thread and the discourse where we keep answering questions and posting, I don't know, tools and stuff. And so it might be worthwhile to check this thread out as well. What are discrete global grid systems? So the Open Geospatial Consortium, which is a non-profit, internationally active with more than 500 members across the world, universities, government agencies, private industry sector, and so on. The working group there defined the discrete global grid system as a spatial reference system that uses a hierarchical tessellation of cells to partition and address the globe. So in the wider sense, we're really talking about not only one grid at one resolution, but once we have several resolutions, then together they become a system of global grids. So the easiest, most sort of natural global grid that you might sort of understand is, of course, as we can see on the left side, the datacubes. They're basically also a grid, a system of grids defined by the degrees of latitude and longitude. But as we can already see here towards the globes, the classical projection issues, the cells, the areas that each grid cell sort of covers becomes smaller and smaller, and it's larger towards the equator, where on the right side you would see a hexagon-based DGGS system that actually smoothly covers the whole globe, where each cell is roughly about the same size. So if we then add additional resolutions, we'll come to that, we have a discrete global grid system. So how would one implement that purely methodologically? So there's Kevin Saar, was one of the early pioneers to make that actually computationally happen. And he wrote in an article sort of a systematic implementation guide in a way. So at first you need a base shape. So that's also called a platonic solid. That is basically a shape like we can see here, the icosahedron in the bottom, that can be used as the base onto which we start building the grid. And then this base shape has to be oriented. Like a cube, you would maybe imagine a cube as a base solid. If you rotate the cube, it actually has then different properties wherever you sort of anchor it, right? So that would be the orientation. Then we need a hierarchical spatial partitioning method, and that is defined typically on the face of the base shape. So if we, in this example here, we would say then, okay, we subdivide the faces of the icosahedron with triangles in order to build a smooth network of triangles that completely and continuously cover the globe. And when talking about hierarchical, that would also mean that we would have triangles at smaller resolutions and at higher resolutions that have a sort of a predictable relationship to each other. And then we need a method for transforming that into the corresponding spherical or ellipsoidal surface. That's usually still a projection, but that one that is used in per face, and it's sort of for the whole globe. It's not the classical projection that we sort of roll out a raster that is a flat map for the whole world. Yeah, it's only for each phase. And then a method of indexing the grid cells, right? That's like there are different ways of indexing. So as a summary, we can see there's actually different base solids or platonic solids, base shapes useful. We can start with pyramid or cube or octahedron, 10-phased or the 12-phased icosahedron, dodecahedron, and the 20-sided icosahedron, if I'm not mistaken. Then we need a subdivision shape, and of course there's classically squares, but of course hexagons have been really popular, and they're also very practical because they are like quite an efficient shape in terms of sort of the nature and around the globe. And of course triangles there because you can always build hexagons out of triangles. So triangles are very practical. So then you would need an indexing scheme so you know which cell, which triangle is at which location in the Earth. That becomes a really important and really useful property because then you can always say this location is here based on the index of that, the ID even of that triangle or hexagon. And there's different indexing methods depending also on the type of tessellation, for example. So you have a hexagonal three-axis indexing or a cube-based classical quad indexing. Triangles actually also really nicely quad index, or you can use space filling curves like Hilbert or Morton curves. So each of those is not necessarily mutually sort of recombinable. Some things only work with certain solids or certain shapes. Here's a nice other visualization of the base shapes and how they basically get unfolded, and actually in memory or in the indexing system it's based around this way of unpacking. Okay, what is actually DGGS used for? So classically discrete global grids have been really used for aggregation, for binning and aggregation, because we want an equal representation of the aggregated data around the globe. And if we think of the classic rolled out raster, then we can't really consider, as I showed in the first, the gratitudes towards the poles, they get smaller and smaller. So the binning is not representative for that area anymore in comparison with cells that are closer to the equator. So that's why DGGS is, because they have this property that they're comparatively even around the globe and reliable, that they're really good for binning. So this picture is from the H3, Uber H3 website. And as you can see, Uber developed H3 as a spatial reference system really targeted for their use case, which is on the city level, to aggregate supply and demand for rideshare, right? So, and this way you have also the advantage with hexagons that the distance to the center of from one hexagon to the next one is approximately always the same. Anyhow, to bin points into hex bins has also been really popular, but some hexagons are just better hexagons because they can be spread around the globe and are still sort of keeping their shape and their area. Then secondly, of course, polygons. We could also consider lines, but lines are sort of a particularly special case because they still have only these 2 dimensions, and actually one, well, because they're so thin, you would have to decide how small you make a field like a cell in order to represent them. But in a similar situation, we also run 2 polygons to fill a polygon with these cells just in order to represent the polygon in that DGGS, in that grid. You would have to decide if you use at a certain resolution, like we can see on the left side, or if we use like a so-called compact filling. That is possible. It comes with its own trade-offs. Let's keep it by that. And of course, a representation of a raster. So this is basically summary of the Copernicus land cover in equal area hexagons, which each of them having roughly 9 square kilometers of area. And No, actually, it's probably 9 kilometers across. So maybe around 80 square kilometers roughly. Yeah, anyhow, so this is, if you would use this Copernicus Landcar, which is global, you could, of course, go on and go on, and the cell size would always be, you could nicely wrap it around the globe. So that's a bit of a like, hey, hexagons, everybody loves hexagons, really popular lately. So, and that maybe also relate to things you might have seen in the news or on Twitter or, so some of the bigger software platforms in geospatial have come to say, hey, we speak hexagons. But what that here in this particular case really means is actually this one particular system, which is this Uber H3. And they have built certain indexing and data storage stuff around in their platforms, or they provide this type of conversion between, typically only between points and the hexagon addresses. So, but also in the literature, it's becoming more recognized, not only on a theoretical level, but also on a more applied level. So over the last 2-3 years, this is just a selection, but I think this is a really good representative selection. It starts on the top one here. We have a datacube perspective on global grid systems. And most of these folks here and the authors, they are also the chairs or the sort of the charter members of the Open Geospatial Consortium, OGC, DGGS working group. So there's a working group, although they focus more on API access to DGGS data, not so much on the computational grid mechanics in the lower end that you might be now more interested in. Then the second one is, for example, a DGGS-based environmental analytics system, and it would work this way. It ingests data, land use, climatic, and so on, and it uses the reliable, the predictable, the grid, the structured grid as the base reference. So whatever different type of data, rasters at different resolutions, observation data, and they get nicely put together into the joint spatial reference system that is valid across the globe. So, and then you can do cell-based in a way like raster algebra, nice analytics like map algebra type of analytics. Furthermore, here intelligent geospatial risk analytics. That's again, it uses a DGS library as a means of aggregating and pre-processing data and then running probability and machine learning analytics to see at which areas it's more risky for boats and in which are less risky. And then a similar here from the EPA, I think this guy, again characterizes coastal environments, and that is mostly on nutrient fluxes, pollution intake from rivers into the estuary, for example, and also uses a discrete global grid as a reference system for data ingestion. And then last but not least here, humbly myself, we did a comparison between different open source available discrete global grid system softwares. And this is something I go on also a bit more in this presentation to show also later. And also these open source, this is sort of my intrinsic wish. That's why I also engaged with the Pangeo community. And in this thread, in this discourse thread before, all this information is there. And I'm not the greatest programmer, so I would, of course, appreciate support in some way, maybe some hints here and there, to make those things more easily accessible through the Pangeo ecosystem. And in order to really test the value on the usability. And then a really nice X-course here also in the business world that I actually use DGGS things internally. So it's not so much that they use that as the platform, like outreach wise, but because they have to integrate data from different sources, that be satellite data at different resolutions, like land use data, which often comes also in polygon data from the national agencies, in order to use that as the internal reference grid to make those types of environment-based management and decision support. So here, Net Carbon from France here, shout out to Basile. They use, here you can see hexagons, and Arbonix is a new startup in Estonia, where we have been supporting a bit for afforestation and suitability, and particular suitability. And this is a classic raster type algorithm, but if you want to scale that up to large areas, you run into the distortion issues. And if you want to have post analytics, then it would be great if all the raster cells would still have reliable equal area type of properties. So when I talk about this DGGS, it's not only it's that useful DGGS software really, and that's open source. So as I mentioned, Uber H3, here's really my disclaimer, important. H3 is not equal area. I'll come to that a bit later with a nice plot. But it is one of the most popular and most widely available software libraries, and it's really an acknowledgement here right now. It's almost in every library, in every software, in every programming language, you will have a binding or an implementation for H3. So that's really good. So that's sort of the example where we should go with some of those DGGS systems ideally, but then of course some that are equal area, right? So because for many scientific analysis, we really want to have normalized towards area, and then we want to be accurate as possible. Our heel pix is basically a inversed heel pix. Heel pix is a NASA projection, NASA, that looks towards the sky and thus subpartitioned the view towards the sky. You can also think of the sphere. And our heel pix did it just inverse, like towards the planet. It's cube based, but for some reason they did some really good magic, and it's really a real proper equal area discrete global grid system. The reference implementation is in Python only. I currently play around maybe with a Rust port, and then you can have WebAssembly and C bindings. I just don't want to. I can't do C or C++ programmings. Google S2. There's a nice backstory. If you know Pokemon Go, actually internally, supposedly there were really good case where they used Google S2 for all this spatial indexing and sort of batching and subpartitioning. Also, Google S2 is not equal area, but it's really fast and robust, and it's actually more used for geometry calculations on a sphere. And here we come also a little bit to the point, depending how geodatic your heart beats. Our heel pix supports ellipsoids, and most other softwares are based on a sphere. Just saying. OpenEager was actually developed through a company called RiskAware, and it is made available on GitHub, and it supports triangles and hexagons, but it seems abandoned. Although we got it to work in some tests, it has a Python API, but it's an Eclipse project. It's a bit difficult to set up, and it's very tightly sort of linked with an old version of GDAR that always brings sort of problems. And then we have DGGrid. So DGGrid is actually an advanced command line utility, less than not a library as such, but it's very flexible. It has very advanced features to create different discrete global grid systems: hexagon-based, triangle-based, diamond-based, and then either shape preserving like Uber H3, or equal area preserving. So that's really powerful. In a way, it's sort of a bit of the let's say the scale, sort of, the bar where it should ideally be a equal area hexagon-based DGGS. So there's a couple of adaptations or wrappers. So DGGrid for R from Richard Barnes. So that's a really good C++ based R wrapper. So you can directly tap. So he did some additional modification. You can directly tap into some of the library functions. But of course, in the R community, it's obviously used for statistics, for binning, and then for statistics. It's not, I think, so much used for building geospatial applications or large workflows as such. Sort of a one-way, I'm inclined to say like a one-way street. And then two Python wrappers. So one is this PyDGGrid, the second one here, is similar, I think, try to work around the bindings like DGGrid for R, and it's used as PyBind 11 and FFI and so on. But it's really hard to get to compile and to work. And then, because as I mentioned, I'm not the greatest programmer, so I built like a DGGrid for Py tool, this one here, that is basically a really simple Python wrapper that creates this config file to run DGGrid, like to create geometries, to bin data, and then it instructs DGGrid to do its thing, and then you can load it back into a data frame, for example. Right? So at least it did the things that I needed. So they all share certain API similarity if you talk about the software side of things, right? So we have DGGrid, RHealPix, and OpenEager, as they are a bit more flexible and they support, for example, either different DGGS systems or reference sort of shapes, or you can also technically, in RHealPix, you can technically provide any ellipsoid. You could technically build this for a different ellipsoid, even for Mars, or if you wanted to. So except H3 and S2, they are sort of, they have this one, there is a fixed rotation, everything is fixed where the corners are and so on. And then of course the main activities that are typically done is code a geolocation into a cell ID or cell object. And this way you can always, even like we saw on the one, even if a couple of points within one cell, they get all coded to this one cell. And then you can do a group by the cell ID and could do like a mean or a mode or median, for example. This way you could then build your aggregations. And of course, in reverse, the cell object or cell ID to a geopoint, which will be the centroid of that cell, or the outline of that cell polygon that is either square or triangle or hexagon. So these are basically the main things that all of these support. And of course, then when it comes to, let's say, spatial analytics and a little bit navigating, neighborhood and so on, you can query what are the neighbors of that cell. You get the cell IDs of the neighbors, child and parent. And here we go then again in terms of resolution. Higher resolution is bigger cells, smaller resolution, or actually other way around. Higher resolution, you have lots of cells, and then the parents have lower resolution and often encompass the same area. And then those sort of utility functions like region fillers, like I showed with the polygon, for example. And that's actually quite interesting if you think of, because currently in the geospatial world, we work either with multidimensional continuous data, like we call it, let's say, raster data or data cubes or those type of, or with like vector discrete data, like either points or polygons that are very specific, sort of, But within a DGGS, in a way, it's really like a good integrator to get data all into the same reference, So one of the things regarding those IDs that is really practical, so when I'm saying about software support, so H3 and actually also H2, they are really, they're really well supported across the software world. So there's this really cool visualization JavaScript library, Kepler.gl. It uses WebGL and it's really high performance. And you can load data into it, and it's only ID based. Now I can show that later. So like you would have a list of data, and instead of having long coordinates, you have the ID of the cell, and this way you can build like a continuous visualization like that. So how do some of those look, some of those DGSs, if we wrap them around the globe? That will, for example, look like that. Here, H3. And if we talk about parent-child relationships, and sometimes you come to like, oh, what is the aperture? The aperture of a system. Aperture is related to how many cells from one resolution step to the next finer resolution step would encompass, this parent-child relationship. So in H3, we can see the red one and the smaller blue ones and the really small ones. You see this is 3 resolutions. And the red ones, so it has aperture 7. That means 7 child cells encompass in one parent cell. So that's aperture 7. And then the next resolution, again, you see this hierarchical really. So one thing with those hexagon based ones, you can see, I'm not sure, do you see my mouse? So there's where the is one pentagon at the corners of this base solid, which this icosahedron, where those corners are. This is where there's always like 12 hexagons, 12 pentagons somewhere across the globe. Okay, so and then we have hexagon aperture 4 and aperture 3. Obviously, the hierarchy doesn't work as well in those hexagon apertures. So then open eager with on the lower left with triangle tessellation. It's an aperture 4 because always 4 triangles make up the next parent. So that's very hierarchical and fully congruent, meaning that the area is fully covering. Then we have our heel picks, and you can see it's quite curious because it uses a mixture of shapes. So like up to I don't know what this the higher latitude and the lower latitude here, it actually uses squares, and it's an aperture 9. So always 9 cells make up one parent. But then here in the top, in the cap, basically it uses so-called dart cells, those like those tilted trapezoid ones, and triangles, and on the top they actually have circuits. But for all of these, this equal area property still holds true. It is, in a way, it's a bit difficult to imagine if you see different shapes, but each of those cells has actually the same area. And on the right side, just exemplary Google S2, which is actually only cube sphered. Is a cube projected into the sphere. You can see that here at those corners, and it's aperture 4. So here a different, how does that look like with like some actual sort of real world data? So this is the city of Tartu where I'm currently residing, and this is the land use data based on the European Corinne land cover. And here on the left side you have the number, the different type of DGGS system. And then it's just basically aggregating across the resolutions to the smaller resolutions upwards, basically. So I sampled the land use at a comparatively high resolution from on the left side, and then as we walk through the increased resolution to the right, based on the aperture, you can see then a higher aperture means, of course, also quickly higher steps in aggregation and sort of abstraction. So you eventually don't keep the detail so long as you zoom out. So that can be a thing or not. That's if you want to do aggregations and you walk through different resolutions. That's sort of just an interesting concept. But it's like with raster, at a certain fine resolution, you actually don't see the difference as such. It's just nicely sampled raw data. Okay, so as I mentioned, I always talk about equal area, not equal area. So because it's sort of all based on statistical and spatial analytical sort of use cases that are on a reasonably large scale, where any raster or any other actually projected coordinate reference system would cause distortions, so that summary aggregation across that are sort of normalized towards area don't really hold true enough anymore. So we want to have a spatial reference system for data that is reliable across the globe, also for the Arctic and the Antarctic regions, so that we can do, I don't know, species sampling, observation, aggregation, binning, and so on, that this actually stays true to the surface. And then if we want to, of course, correlate that with other variables, then we also want to have them in a similar, easily accessible and relatable format. So we did in this last paper that I showed, we just did the comparison that we generated the geometries, and we did that all in Python and with Dask parallel, and then that was quite a big effort, because of course the number of cells gets really quickly really big, and right now we're not really efficient in dealing that with like really big numbers when you have like several million cells. But if you think of a raster that has just 1,000 by 1,000 pixel image sort of resolution, then that's already a million of cells. But having them as discrete items is maybe something that needs to be sort of improved somehow. I'll have that later in like challenging areas. So as we can see, the hexagonal ones here, ICEA is the inverse Snyder equal area projection used per cell. The ICEA ones, they are always really good in terms of area preservation. As you can see, ICEA triangle based one for OpenEager, or ICEA hexagon based from DGG Grid. They have really few distortions. And those outliers here, they are related, as I said, to those corners of the icosahedron. There you have some stronger sort of distortion. So what H3 did, they put the icosahedron they rotated it that all the corners are in the oceans, or mostly, so that there won't be cities, so they don't run into that problem. Not so bad, although for H3, if you see in comparison, the distribution is already much wider. So technically you can have quite big distortions, up to 30-40% already within 1,000, 2,000 kilometer distance, that the cells will have that sort of difference in size. And then curiously, our HealPix has this really superb area preservation. It's quite curious. And then Google S2, I wouldn't actually consider Google S2 as a DGGS really as a use case. But I mean, you can create those cells, and they have IDs. So in a way, yes, but it has, of course, because it's not meant for that. It's more meant for general spherical based calculations. So also big distortion. And how does it look on the globe? That's here for H3. And you can really see, if you count that here, 1, 2, 3, 4, that's, I mean, for each of the areas, you see the blue areas is really the corners that are coming out. And at the center of the triangle base faces, you can get 2 large areas, and at the corners, you get 2 small areas per cell. So this is made at a quite high resolution. So that's still plotting the cells. You can't see the cell individually anymore, but here's a histogram that relates to the colors also on the right side. You can see, so H3 has some significant distortions if you want to go larger area stuff. So here's the comparison for the other ones again. DGG Grid hexagonal is really reliable. If you look really closely, you might see a few of the blue points, which again is the hexagon corners. OpenEager has some maybe let's say instabilities the way they generate the grid. So you can see along some related to the geometry of the underlying base solid. Sort of, it really goes along some sort of break lines, sort of. But overall, actually also quite clean. Our HealPix also very reliable, almost zero distortion. And then Google S2 also quite strong. You can also see nicely the pattern, so that's quite interesting. I would quickly like to mention that we developed together with Pangeo and another large consortium, we developed a grant and we submitted that to the European Union for a big call. Unfortunately, we didn't get funded, but we wanted to share, I mean, the idea anyway. And so if you are interested in that, you can, of course, reach out to us, and we're aiming to resubmit. So, but we might have to overwork the grant a little bit anyway. And so if you're really interested, you're most welcome, of course, to reach out, and we can see then if we can will they include you, for example. So actually, the United Nations have actually the Committee of Experts on Global and Geospatial Information. They actually have developed a global geospatial statistical framework. And actually there they mention even DGGS as a common geography will ensure that our statistical data is consistently geospatially enabled, and that users can discover, access, integrate, analyze, and visualize statistical information seamlessly for geographies of interest. So here we really run also into the situation that even for the Sustainable Development Goals reporting, and anyway for all these aims to improve, I don't know, soil erosion, drought, all these effects that need to be sort of geographically but also statistically sort of analyzed. And in addition, we need to combine also tabular and spatial data. And as we have these different spatial units like raster pixels, or for example remote sensing, or various vector points, lines, polygons, geometry, cadastral or administrative units, like agricultural fields or something, they're varying in size and shape. And so that's actually quite a challenge. So here DGS are recognized as a really good way of a spatial statistical framework, really. And how is that? We have many partners in that consortium, and also many European statistical offices like this, Norway, Estonia, and so on, Portugal. And they have the situation that they have to do the census reporting, for example, and those type of things within their country. That has to be, of course, abstracted at some point, because they're not supposed to show all the where the people live exactly. So that's usually, but zip code and administrative units, as they vary in size and shape, is a really unpractical and distorting means of showing, like for example population densities and those type of things. So instead of having to normalize per different type of spatial unit, why not using a DGGS? So they have actually already looked at that, and they run now also into the situation, okay, you can do it if you do the normal grid. Many countries actually have their own statistical grid. But in Europe, you have like 25 more countries. They then have to report those national statistics, population statistics, and so on, to the European Union, to the European Commission. And the European Commission has its own spatial sort of statistical grid. And if you would have to aggregate them, there's a lot of resampling going on. If now all would use the same grid, then why not use a globally relevant one? In addition, for the European data market, we aimed it like this because these cells have distinct, unique IDs, as mentioned before. And this way you could also have distributed services from where to aggregate data for the same cells, for example, right? And this was like one of the other things that we were hoping, or we were aiming for in this grant. So European strategy had these data spaces and data products, data value-added products, like right now all these satellite startups, but then you have to download either these huge satellite images, or only you have to send your polygon, you get something for your polygon. But why not something that is even more flexible, where you can load small portions based on a series of IDs only, for example. And DGGS software, as we saw, is now increasingly becoming available and usable, and it would be really good for aggregation and data fusion. And you can extract or align tabular data together with spatial data, which makes it really good for ML processing, even non-spatial ML processing, where you just have columns versus rows, makes it quite nice. And we wanted really to pitch that to work with the Pangeo community, with the OGC working groups in order to mature the software ecosystem and around DGS and API standardization. So that was the pitch for that grant. So there's lots of things that we want to sort of push forward, but we need more momentum. And there's some references that I used throughout the presentation. You can look them up then. And then I would maybe show a little demo. So DGGS in smaller scales works really fine already, but there's still some challenges, and I'll sort of iterate through it a little bit while I do the demonstration. So tooling, as you saw, there's some libraries, and I will show them how to use them. But some work better, but they don't have the properties we want, or like let's say I want, equal area. And then we have some tools that do have that, but they're not so well integrated. So there's this. That's why H3 is so extremely popular right now. So everybody uses it because they love hexagons. But on the other side, it's not equal area. So you have to be really careful for what use cases you use that. And as I said, Uber only uses it on the city level, so you don't run into those large scale differences. And of course, it's a bit of a chicken and egg problem because currently we don't really have data in DGS format. So we always have to convert it. And this conversion feels really heavy and inefficient. So we can't really play, hey, it would be so easy if we can just get data for those IDs, because we don't have that, because we always have to convert it. So that's why we have to come up maybe with a bit more efficient workflows of either we convert all the data into DGS, but I think that might even not be feasible. So, or we index sort of on the fly, like we still have like our let's say ZAR or Parquet lying around, and then whenever there's coming queries, then we do like batched, partition based on the parents or something, and then pull it after another to whatever analysis we want. And of course, we would have to think about storage and access, and then Pangeo is looking at that anyway. Here, just again that link. Wait, actually, we don't need that. I'll now stop sharing this one, and I will show now my screen here where I have that one. So I have here a couple of notebooks. They're quite simplistic, and I just showed to generate some geometries, how to use the address conversion, geo to cell, cell to geo, how to put it on a map, and some tooling that is not as intuitive, which we hopefully can improve through Pangeo, Conda packaging, and so on. And I will make those available through a GitHub and research objects thing, so that will be for free use and exploration. So firstly here, really quick H3. And H3 is just really, as I mentioned before, easy to use. So I have here my desk geo Python environment, and so I import H3. H3 had different APIs. You can also have like a NumPy suitable one. Then the IDs will be integers, but in this case, it's this classical here hex-based ID. Okay, here's our example. We make a like a point and a resolution. So you always have to sort of know a resolution. You have to decide a resolution. So there's also these tables of resolutions, H3 Geo. Each of these coordinate reference systems, these spatial reference systems, has a table like such, which resolution, and then how many numbers of cells would cover the globe, and there should also be here. There's even now a caution. That was not before. That's nice. Caution. It's not ideal. And this is also a average, right? It's not the min and the max, it's the average. So here we would have around 70 hectares roughly. Wait, 700 hectares at resolution 8. Okay, so that would be that cell, and we would then use the API geo2h3, coordinates and resolution, and you get, the ID, and the ID is of type string, and in reverse, you would just take the ID h3 to geo from the ID, and you get the coordinates, right? But those coordinates are of course not identical to those, because this is now the centroid of the cell. So this is something under consideration. If you bin data, you don't need to go back down there. But the location of the cell is of course still important, because whichever ID you use, it will be somewhere on the Earth, which is quite nice. So you can always go back and forth. And you can also ask, instead of the centroid, you can get the boundary. And the GeoJSON parameter here is, for example, is just for the coordinate order, if that's this GeoJSON standard. So if you would then make it as a shapely polygon, it's just here Python shapely polygon, I will just nicely show. So I use here Folium. Folium is a Python library that basically creates a little leaflet visualizations. So I'm just here doing some conversion to put this on a Folium map and give some colors. So that's basically just, for each polygon. It's a bit inconvenient. It's more like for the visualization aspect here right now. It's a function that I can give it a list of hexagons, and it will create the necessary object to put it on a map. Another thing is also within this ID here, right? Within this ID, as we put it in before, the resolution is also known. Yeah. So going back from the ID also knows the resolution. So you have all this additional meta information basically encoded in the indexing system. You can even ask it what's the parent, the higher resolution, and you can also ask it its children, right? So if we here, for example, okay, give me the parent, then we have this one, the parent ID, and if you then ask the resolution of this parent ID, it's actually confirming that you get the lower lower resolution. And then just let's put it here on the map. This is this function here where I just give it the ID, and we end up here in Tartu, right? So if you have any other, you could just play dump here, and I just put a randomly different number. I don't know where I end up now. Where is that?
Alex, sorry for interrupting.
Yeah.
Just let you know that we have 8 minutes left.
How many?
If you want 8 minutes.
8 minutes. I think.
Yeah. If you
think
want
I
to
can
have some question from the audience later, but
okay.
Yeah.
Yep. Thanks. So that's basically the general mechanics of that. Then in another example here, what I said, this DGG grid software is a command line tool. So I wrote a little a wrapper around it, and you have to have DGG grid on a computer. I used the Julia building system once to get it sort of distributed, but that currently doesn't work. So I would really want to have this as a conda package. And then once you have this tool, so I have it on my computer here right now, so I can then just run this and say I create this type of system with this resolution, and you get a geodata frame. I'm just putting it on a map here. So one of the visualization things in a normal GS is that things that cross the data line are really difficult to show. So I'm filtering them out. Then of course you end up with but with smaller resolutions, you don't see that so much anymore. Then I told also our heel picks. And here you can actually say different ellipsoids if you want to try them. And I do the same thing again. I'm generating the geometries just for a whole level in the world. This is a nice geo views view here with the orthographic projection. And then this way, basically, you look at the H3 and the our heel peaks globe. And then for DGG grid, I generate, oh, that's a lot here, the resolutions for the DGG grid at aperture 3 and hexagons, triangles as well. So this just, you know, the geometries. So in the last example here, I have, I create again the geometries and I'm loading. So this is a bit higher resolution. This is just for fun, the plotting. The population data, it's a raster, global raster, which I'm then sampling with geometries. And then I classify with map classify. And then, you know, like this is then actually now the global population grid sampled into a equal area grid. And as you can see, with Europe, with India and Africa here, high resolution, high density, and then of course in the Arctic, not so high density, obviously in the Sahara. And last but not least, here those tables, this is just for fun. You can see if you would have this type of data table with the ID and various variables, then you can, this would be a format to share and load you know, big collections of data, similar to like ZAR, but each cell is sort of, you know, now in this DGGS format. Yeah, you don't have to transmit the geometries as such. That's that. Yeah, thanks. Yeah, so that was a demo. And then again, I would just, you know, put this back here for the outreach, get in touch here or by other means. And thank you very much.
Thank you, Alex. It looks that these notebooks, maybe if they are available, then we can share in the notes later. So
yeah.